Imagine an artificial intelligence system as powerful as today's most advanced AI models, but small enough to fit inside a coin, fast enough to react instantly, and efficient enough to run on almost no electricity. It sounds like science fiction, but many researchers believe this technology could arrive sooner than fully practical quantum computers. While the world is fascinated by quantum computing, another revolution is quietly taking shape inside research laboratories. It's called neuromorphic computing, and it could completely change the future of artificial intelligence. For decades, computers have become faster by making smaller and smaller transistors. But that strategy is reaching its physical limits. Engineers can no longer rely on simply shrinking hardware forever. Instead, they're asking a completely different question. What if computers stopped thinking like calculators and started thinking like the human brain? The answer to that question may reshape everything from robots and self-driving cars to medicine, space exploration, and even the way AI runs on your own smartphone. The story actually begins back in 1971 when electrical engineer Leon Chua proposed the existence of a mysterious electronic component he called the memristor, short for memory resistor. Unlike ordinary electronic components, a memristor could process information and remember it at the same time. In theory, it behaved remarkably like a biological synapse inside the human brain. For nearly 40 years, the memristor remained nothing more than a mathematical prediction. Many scientists considered it an interesting idea that would never become reality. But everything changed in 2008, when researchers successfully demonstrated a working memristor. Suddenly, an idea that had lived only on paper became one of the most exciting building blocks for future computing. Around the same time, scientists began looking more closely at how the human brain actually works. They realized that our brains don't compute by moving electrons through dry wires like traditional computers. Instead, neurons communicate by moving ions such as sodium and potassium through a watery biological environment. That discovery inspired entirely new approaches to hardware, including ionic and liquid-based electronic systems designed to imitate biology itself. To understand why this matters, we first need to understand the biggest weakness of today's computers. Nearly every modern computer, smartphone, and supercomputer still follows the von Neumann architecture, introduced by John von Neumann during the 1940s. In this design, the processor performs calculations while the memory stores information. The problem is that these two parts are physically separated. Imagine a chef preparing dinner. Every single ingredient is stored in one room, while the stove is located in another. No matter how talented the chef is, valuable time and energy are wasted constantly walking back and forth. Modern processors do exactly the same thing. They spend enormous amounts of time moving data between memory and the processor. This problem is known as the von Neumann bottleneck, and today it limits everything from smartphones to the world's fastest supercomputers. During the late 1980s, computer scientist Carver Mead realized that nature had already solved one of computing's biggest problems millions of years ago. In the human brain, neurons process information while synapses store memories in the same place. Inspired by this, Mead introduced the idea of neuromorphic computing, where computers mimic the brain instead of relying on traditional designs. Today, with Moore's law reaching its limits, engineers are turning that vision into reality. Unlike conventional processors that constantly run on a master clock, neuromorphic chips use spiking neural networks, or SNNs. Artificial neurons stay inactive until important information arrives. When a signal crosses a certain threshold, they briefly fire an electrical pulse, called a spike, then immediately return to sleep. This event-driven approach means the chip only uses energy when it actually needs to. The result is incredible efficiency. While the human brain performs complex tasks using only about 20 watts of power, today's AI systems require massive data centers that consume millions of watts. By combining memory and processing in the same location, neuromorphic chips eliminate the constant movement of data, dramatically reducing power consumption and bringing us closer to powerful AI that can run directly on small devices. The second secret is asynchronous computing. Unlike traditional processors that constantly consume power because of a master clock, neuromorphic chips only activate when something important happens. If there's no new information to process, they simply stay asleep. An artificial neuron wakes up, performs its task in milliseconds, then powers down again. This event-driven design makes these chips incredibly energy efficient and could allow future AI devices to run for long periods using tiny renewable energy sources. They're also far more resilient. A traditional processor can fail if a critical component breaks. Neuromorphic chips, however, work like the human brain. If one group of artificial neurons is damaged by heat, radiation, or wear, nearby neurons automatically create new pathways. Instead of shutting down, the system adapts and keeps working. Even more impressive is how these chips learn. Today's AI models are trained for weeks or months inside massive data centers before they're deployed. Neuromorphic chips can learn directly inside the hardware itself. Using a brain-inspired process called spike timing dependent plasticity, or STDP, connections between artificial neurons become stronger as they repeatedly work together. The hardware literally rewires itself through experience. Imagine a robot stepping onto ice for the first time. Instead of waiting for a software update, it could instantly adjust its own neural connections and learn to stay balanced. This is made possible by a revolutionary component called the memristor. Unlike ordinary memory, a memristor physically remembers the electrical signals that passed through it, even after the power is turned off. It combines memory and processing in the same place, just like a biological synapse. That breakthrough could lead to smarter drones, advanced prosthetic limbs, autonomous space probes, and AI devices that process information locally, protecting privacy while using only a fraction of today's energy. Neuromorphic computing is no longer just a laboratory experiment. In Spain, researchers have already developed intelligent neuromorphic chips that can analyze water quality in real time. Instead of simply collecting data, these chips learn from chemical signals, make decisions instantly, and consume very little energy. Technologies like this are already helping improve agriculture, aquaculture, and environmental monitoring. But despite this incredible progress, major challenges remain. The biggest isn't the hardware, it's the software. For over 70 years, programmers have written code step by step using languages like Python and C++. Neuromorphic chips don't work that way. Instead of following fixed instructions, they learn through experience, making programming feel more like teaching than coding. There's also the challenge of trust. Because these chips constantly adapt and rewire themselves, it can be difficult to understand exactly why they made a certain decision. That raises important questions for self-driving cars, medical devices, and other critical systems. Even so, the potential is enormous, as AI continues to consume more electricity. Neuromorphic computing offers a far more efficient and sustainable future. Instead of simply building faster computers, scientists are building machines that think more like the human brain, and that could change technology forever. If you enjoyed this video, don't forget to like, subscribe, and turn on notifications for more videos about the future of technology. Thanks for watching, and we'll see you in the next one.